Hello, everybody. I hope you're doing well. Today, we will talk about the public key crypto system based on discrete logarithm problem. As you remember, last time we were talking about RSA. It is chapter 6, 7, and rest. We will talk about public key cryptography or asymmetric cryptography. Last time I gave an example about the protocol of RSA. Now I would like to talk about Diffie-Hellman key exchange. Specifically, everything is relying on discrete logarithm problem. One more thing I want to recall for you. What is the key point of public key cryptography? Yes, it is about let me just open. It is one-way functions. Yes, one-way function. Let's recall what is one-way function. One-way function. Yes, one-way function. It is evaluating the function f of x is easy, but the inverting it, f inverse of x, is hard. All of them all our public key cryptography relies on that scheme. So for example, for the RS, and I explained that there are three one-way functions. First one is, as you remember, factorization is hard. Factorization is hard. And for example, if you are given n, and this has to be factor of p and q, evaluating p times q is easy. This is multiplication is easy. But what is hard in here is given for you, given n, find p and q. This is called hard. Yes, and this is relies on the RSA relies on that one. Yes, hard. Yes, the example for the factorization, it is going to be the RSA. The second one-way function, it is discrete logarithm problem. Do you remember? I talked about that. Discrete logarithm problem. This is hard. What is hard? First of all, let's talk about what is easy before I will talk about hard. Evaluate, given for you the base, given for you the x, and given for you modulo p. This is easy because I can use a square and multiply algorithm, and it's doable. Yes, it's doable. But what is hard in here? What is hard in here, given for you y, and also given for you the base, another element g, modulo p, and we have to find the exponent x. This is hard. This is the logarithmic function. We have to find the logarithmic function. This is hard. And the third one, I talk about the general discrete logarithm problem, which is not modulo p. Maybe it works on elliptic curve, any other things. Its idea is the same, but we are not working with the ZP. We will work of generalization of the groups. And I will talk about in chapter 9. And I will talk about this schema in later of this chapter. Yes, chapter 9 and 8, let's say. Okay, so this was the recall about one-way function and why do we need it. All our scheme of the public key cryptography relies on this one-way function. Now let's talk about more in discrete logarithm problem. First thing is what I want to talk about Diffie-Hellman key exchange. Of course, after I talk about this protocol, I have to start with mathematics before I will continue talking about further. Yes, I will talk about finite groups, cyclic group. Then the next thing is I want to talk about discrete logarithm problem and Diffie-Hellman problem. And this is what is my goal for this lecture. The next is general discrete logarithm problem, security of the discrete logarithm problem, and Diffie-Hellman key exchange. Then I will show you how to do the encryption with El-Gamal and so forth. Let's talk about Diffie-Hellman key exchange. It is it is proposed in 1976 by Whitfield Diffie and Martin Hellman. And they both of them are introduced for us a public key cryptography. And I want that you will watch this link. Let me just watch this link. Open. Does it play?
Between the Soviet Union and the United States. It was clear that the next global superpower required the ability to both launch and successfully defend nuclear attacks from intercontinental ballistic missiles. In North America, the most vulnerable point of attack was over the North Pole. So in 1958, a joint effort between United States and Canada was established, known as NORAD, or North American Aerospace Defense Command. An important line of defense was the semi-automatic ground environment. It was an automated system of over 100 long-distance radars scattered across North America. They were connected to computerized radar stations that transmitted tracking data using telephone lines or radio waves. All of this radar information was fed into a primary warning center buried a mile deep inside Cheyenne Mountain in Colorado. This application of machine-to-machine communication allowed operators to make split-second decisions using information transmitted and processed automatically by computers. This idea of being online was quickly adapted and advanced by universities in the following years as they understood the potential of computer networking.
The thing that makes the computer communication network special is that it puts the workers, the team members who are geographically distributed, in touch not only with one another, but with the information base with which they work all the time. And this is obviously going to make a tremendous difference in how we plan, organize, and execute almost everything of any intellectual consequence. If we get into a mode in which everything is handled electronically and your only identification is some little plastic thing you stick into the machinery, then I can imagine that they want to get that settled up with your bank account just right now and put it through all the checks, and that would require a network.
Money transfers were just one of a growing number of applications which required encryption to remain secure. And as the internet grew to encompass millions around the world, a new problem emerged. At the time, encryption required two parties to first share a secret random number known as a key. So how could two people who have never met agree on a secret shared key without letting Eve, who is always listening, also obtain a copy? In 1976, Whitfield Diffie and Martin Hellman devised an amazing trick to do this. First, let's explore how this trick is done using colors. How could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on two facts. One, it's easy to mix two colors together to make a third color. And two, given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock. Easy in one direction, hard in the reverse direction. This is known as a one-way function. Now, the solution works as follows. First, they agree publicly on a starting color, say yellow. Next, Alice and Bob both randomly select private colors and mix them into the public yellow in order to disguise their private colors. Now, Alice keeps her private color and sends her mixture to Bob. And Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrived at a shared secret color. Notice how Eve is unable to determine this exact color since she needs one of their private colors to do so. And that is the trick. Now, to do this with numbers, we need a numerical procedure, which is easy in one direction and hard in the other. This brings us to modular arithmetic, also known as clock arithmetic. For example, to find 46 mod 12, we could take a rope of length 46 units and wrap it around a clock of 12 units, which is called the modulus, and where the rope ends is the solution. So we say 46 mod 12 is congruent to 10. Easy. Now, to make this work, we use a prime modulus, such as 17, then we find a primitive root of 17, in this case 3, which has this important property that when raised to different exponents, the solution distributes uniformly around the clock. 3 is known as the generator. If we raise 3 to any exponent x, then the solution is equally likely to be any integer between 0 and 17. Now, the reverse procedure is hard. Say, given 12, find the exponent 3 needs to be raised to. This is called the discrete logarithm problem. And now we have our one-way function, easy to perform, but hard to reverse. Given 12, we would have to resort to trial and error to find matching exponents. How hard is this? Well, with small numbers it's easy, but if we use a prime modulus which is hundreds of digits long, it becomes impractical to solve. Even if you had access to all computational power on Earth, it could take thousands of years to run through all possibilities. So the strength of a one-way function is based on the time needed to reverse it. Now this is our solution. First, Alice and Bob agree publicly on a prime modulus and a generator, in this case 17 and 3. Then Alice selects a private random number, say 15, and calculates 3 to the power 15 mod 17, and sends this result publicly to Bob. Then Bob selects his private random number, say 13, and calculates 3 to the power 13 mod 17, and sends this result publicly to Alice. And now the heart of the trick. Alice takes Bob's public result and raises it to the power of her private number to obtain the shared secret, which in this case is 10. Bob takes Alice's public result and raises it to the power of his private number, resulting in the same shared secret. Notice they did the same calculation, though it may not look like it at first. Consider Alice. The 12 she received from Bob was calculated as 3 to the power 13 mod 17. So her calculation was the same as 3 to the power 13 to the power 15 mod 17. Now consider Bob. The 6 he received from Alice was calculated as 3 to the power 15 mod 17. So his calculation was the same as 3 to the power 15 to the power 13. Notice they did the same calculation with the exponents in a different order. When you flip the exponent, the result doesn't change. So they both calculated 3 raised to the power of their private numbers. Without one of these private numbers, 15 or 13, Eve will not be able to find the solution. And this is how it's done. While Eve is stuck grinding away at the discrete logarithm problem, and with large enough numbers, we can say it's practically impossible for her to break the encryption in a reasonable amount of time. This solves the key exchange problem. It can be used in conjunction with a pseudo-random generator to encrypt messages between people who have never met.
I hope you like this video. They made little bit mistake over there, saying that 3 to the power of, let me just show you, 3 to 3 to the power of 13, not to the power, but it's going to be like 15, is modulo 17. And they said 3 to the power of 15, and it's not power, it is multiplication. Yes, the to the 13 modulo 17, and they want to say that this is equivalent because what happened with exponent, this two exponent got multiplied 13 times 15, and this becomes 15 times 13, so they are equivalent. I hope you really enjoyed from this video, and this video at least gives the idea what is the idea about discrete logarithm problem and Diffie-Hellman key exchange. Diffie-Hellman key exchange is used widely in secure shell, transport layer security, internet protocol security, and all over actually. Why do we need Diffie-Hellman key exchange? As you remember, for the symmetric cryptography, number one problem is how can you distribute your key, Alice and Bob? If Alice is living far away from Bob, how do they share their key via insecure channel? In this condition, the public key cryptography comes to the help, and this is our Superman, specifically Diffie-Hellman key exchange, RSA. Both of them can help to exchange these two keys. Diffie-Hellman key exchange is used for the key exchange protocol, okay? It's not used for the encryption. So for the encryption, we're going to use El-Gamal. For the purpose of encryption of Diffie-Hellman key exchange, we're going to use El-Gamal, which we will talk about in the next slides. Yes. So now let's talk about little bit about Diffie-Hellman key exchange. How does Diffie-Hellman key exchange work? First of all, you already listened the video, and choose a first thing is before you will start it, you have to set up with the key. So we have to choose the large prime P, and the next one is, this is the large prime P, yes, and the next one is choose an integer from this set from 2 till P minus 2. And this has to be a generator. Alpha has to be a generator, which I will talk about what does it mean generator soon, okay? Generator of, let's say, ZP star. I will talk about that, and then we will publish P and alpha. Before we will talk about Diffie-Hellman key exchange, what we're going to do is given for Alice and Bob, P and alpha. P is large prime, P alpha is the generator. This is prime number, and this one is the generator. Okay, now Alice and Bob are communicating. Alice and Bob. Yes, so how do they do this? So first thing is, as you listen that, Alice will choose her own color. I'm gonna call it A. It can be a number, it can be a color. I like to call it color. Yes, this is going to be the color of the Alice, private key of the Alice, and this private key has to be randomly chosen. This is my notation from the set of 2, 3, 3 to P minus 2. Similarly, Bob will choose his own color. I'm going to call B, which is the private color of the Bob from the set of 2, 3. He knows what is P, yes, because it is published. It's everybody knows about this, yes. Everybody knows about P and alpha. The next thing is they have to make mixture, and they will share their mixture to Alice and Bob. They want to come up with the same color, yes. So first thing is, how do they mix it? So Alice will have a generator A alpha. It makes alpha to the power of A modulo P, and this is going to be the public key. This is the public key of the Alice. Yes, similarly Bob will do, yes, capital B. Notice that small a is the private key and big A is the public key. Make sure that you understand that. Alpha to the power of B, which is modulo P. This can be the K public of capital B. Then what they will exchange in here, Alice will exchange his public color, her public color I mean, and Bob will exchange his public color, capital B. Yes, now Alice will get this public color of the Bob, B, and mixes with her own private color, A. B to the power of A modulo P, and this is going to be a common color, AB. And similarly, Bob will calculate KAB. How? He will get the Alice's color, public color A, mixes with his own private color, modulo P, and this is how they got the common color. Now let's make proof of correctness. Is this the correct proof of correctness? What does it mean, proof of correctness? If Alice is calculating, what did Alice calculate? Alice calculated B to the power of A. Yes, B to the power of A. How did B were calculated? This B were calculated from Bob, and it was calculated as alpha to the power of B to the A. Yes, as you remember that from algebra class, these two exponents got multiplied and you have alpha to the power of B times A, which is actually alpha to the power of A times B modulo P. Yes, and this is the key AB. This is Alice calculate. What did Bob calculate? Let's calculate that. Bob get A to the power of B, capital A to the power of B. Capital A were calculated as alpha to the power of A, alpha to the power of A. Now this is capital A and B. As you remember, this has got multiplied, alpha to the power of A times B modulo P. What happened in here, as you notice that these numbers are equivalent. So what happened in here, this is equivalent to KAB, this is equivalent to KAB. What happened is Alice and Bob get the same key, both of them. So this is called proof of correctness. Yes, so and this is the idea of the Diffie-Hellman key exchange. I like to explain with colors, it is more understandable, but of course we are working with the numbers in here. Okay, excellent. So and next slide is explaining to us about the Diffie-Hellman key exchange. Why do we care about Diffie-Hellman key exchange? Yes, so as I explained to you, the Alice is choosing her color, Bob is choosing his color, and so on. They come up with the same shared key. After they got the same shared key, what they will do is, for example, they want to do the encryption. If they want to do encryption, they can use the symmetric cryptography. You remember, this is hybrid system. You can do it. You can make key exchange using public key cryptography, and using private key cryptography you can make encryption. So now you are using the shared key over here, and you can encrypt your message, send the ciphertext, and Bob also has exactly the same key as the Alice. Use the AES inverse, get the message. So this is hybrid system. Yes, this one is Diffie-Hellman key exchange. Yes, Diffie-Hellman key exchange, and that one is AES. Yes, AES. So this is called hybrid system. You are exchanging your keys, and this one is encryption. So proof of correctness I explained on the previous slide. In here also I'm explaining. Now a specific example. Let's say that I'm gonna work with very small number. So, but it of course it is not secure. But if it is going to be big numbers, then it's going to be very secure. So let's say that P is 29, this is prime, and alpha is 2. 2 is generator, P is prime, and before Alice and Bob is communicating, the two parameters are given. Alice is choosing her private color, let's say A. A is 5 from the set of 2 till P minus 2. P minus 2, it means what? 27. Any number between 2 till 27. She randomly choose random number come up 5. Similarly, the Bob choose his own color B, which is 12. Now before they are communicating, they have the base 2 and 29. Alice is mixing her colors. How she is mixing? She's taking 2 to the power 5 modulo 29, and this is gives 32. Subtract 29, it's going to give 3. So Alice is sending A, capital A in here is 3, and Bob is also mixing his color. He's taking the base 2 to the power of 12 modulo 29, and he got, actually this is 7, and he's sending his own public color, which is 7 in here. Now Alice is getting this public color 7, mixes with her own private color, this is private color, 7 to the power 5, she got 16. Similarly, Bob got Alice's public color, which is 3 to the power of 12. 12 is coming from his color, and mixes, it means exponentiation in this condition, modulo 29, it gives 16. So you see that both of them has exact same number without even knowing about that. Yes, and you can check it out, the proof of correctness similarly. So the big idea relies over here, cryptography relies on the how mathematics works, why this is hard, what is going on. We have to talk about little bit mathematics on that before proceeding. Yes, as usually. Let's talk about finite group and the cyclic group right now. First of all, what is the group? I already taught you the groups, yes, several times. In chapter 4 you heard a lot about that. The group is the set of the set with the elements and one group operation. We usually denote it as a group is the set of elements with some kind of operation. This one, yes, this contains elements. This can do addition, subtraction, multiplication, or division, one of them. Yes, let me just talk how I do it on the board. This would be much understandable. Yes, the group. I'm going to do this color. Group is a set of elements, which satisfies the following properties. If A and B is inside of this one. As you remember, the first condition is the closure. What is closure? Closure, it means that if you are doing what we are doing, the group with, we are doing a group with one operation. Yes, operation is some kind of this. So if you are doing A operation B, you are getting actually the C. Yes, and this group element has to be inside of the group element. Second thing is it has to satisfy associativity. And what does it mean, associativity? If you exchange the parentheses, nothing changes over here. Yes, and the third one is the identity. Identity. What is identity? We have element 1id. 1id, it means what? It means 1 if your operation is equivalent to multiplication. This is multiplication. Let me write down like that, multiplication. If it's 0 if your operation is equals to addition. Yes. So what does this mean? It means that if you are doing a operation 1id, you have to get actually a itself. Yes. So what does it mean, a operation 1id? Let's do example over here. A operation of 1id. What does this mean? That if you are doing a multiplication with 1, you have a. If your operation is multiplication, if you have a plus 1, it's not going to give you a, so our ID has to be 0. That's why it's going to be a. So in here, operation is multiplication. So you understand that. The first one is the inverse element. Yes, the invertibility. Inverse. All element has to be invertible. For all a inside of G, what it has to satisfy, a operation a inverse has to give you 1id. Yes, 1id can be, for the multiplication it has to be 1, for the addition it has to be 0. Yes, and if it satisfies this 4 condition, we say it is a group. Yes, this is the group. If it satisfies the 5th condition, this is called the commutativity. We say commutative group. Yes, what is commutativity? A operation B is equals to B operation A. It satisfies 5 conditions, then we say it is commutative group. Yes, commutative group. Yes, so this is about the definition of the group, which we talked about in class. Yes. Now, what I want to talk about right now, I want to do a couple examples. So, examples is, so let's talk about Z9. Yes, Z9 contains elements of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yes, and I'm going to ask you the example 1 in here is, does Z9 under the operation of addition, is it a group? Is it a group? What do you think? Does it satisfy this 4 condition? If you take, what does mean 4 condition? If you take these 2 elements in here, if you add them and modulo 9, is it going to be inside of the group? Let me give you any example. Yes, let's take 6 and then let's take 8. 6 plus 8 is going to be 14. And if 14 modulo 9, what is going to be here? 6 plus 8 is 14. But we are taking modulo 9 right now. What is that equals to? It is 5. Yes. Is this the 5 inside of Z9? Yes, it is inside of Z9. So any element you will do it. If you do that one, closure satisfy. Yes, closure satisfies. Associativity for sure satisfy. Identity, we have it. Identity is 0 in here. Inverse, what does it mean inverse? So if I will take any elements from here, give me any element. Yes, 4. If I will add with something inside of this group, can I get 0 in here, modulo 9? Absolutely, I can do it. It's not a problem. For example, if you give me 4, 4 plus 5 will give you. So the Z9 under the operation from 0, 1 to 9, it is a group because it satisfies all kind of condition. It's not just a group, it's also a commutative group. So in this example, it was in order to make a 0, you could add by 5. Yes, 5 is in there. So the question is over here is, does this Z9 under the operation is multiplication? Is it the group? In this condition, we have to again go back and check that the closure, associativity, identity satisfy. Yes, all of them satisfy. Our identity in here is what? One ID in here is 1. Yes, so the inverse, does all element, if I will choose from here, are invertible? So okay, if I will ask you, does 0 inverse, can you find 0 inverse modulo 9? What does this mean? It means that if I will take 0 times something, it has to give me congruent to 1 modulo 9. Does it gonna give you? Never. It can happen. It doesn't exist. Yes, you will say that this doesn't exist. Yes, so that's why it is not a group, just because 0 is not invertible. Not just 0 is not invertible. You can find more not invertible elements. What are not invertible elements? Invertible elements are what? Elements the 0, 3, because GCD of 3 and 9 is not 1. 3 is not invertible. Actually, sorry, I made mistake over here. Over here, we have to eliminate 9. Yes, it has to go from 0 till 8. So it's going to be the 6. They are not invertible in this condition. So it is not a group. It's not a group. So now I did an example over here, similar example. Z9 is a group. Let me use different color. So Z9 is a group. It's not a problem. How about it if it is multiplication? It's not the group because 0, 3 and 6 are not invertible. That's why it's not a group. And another one is Z9 star. Now we want to use the multiplication. It's very good to use. Yes, we don't want to put it in garbage because of some of elements are not invertible. So what we have to do in this condition, so as you see that 0, 3 and 6 are not invertible. So what we're going to do is we will introduce something like this is called the Z9 star. It means that I will exclude all elements which are not invertible. What over here left is 1, 2, 4, 5, 7, and 8. So what elements I left with in here, I can write down all elements x such that the GCD of I and 9 is equals to 1. So x and 9 is equals to 1. So all elements are invertible. This means that GCD of those elements with 9 has to be 1. Yes, in this condition, the Z9 star is the group. Z9 star will be those elements. Yes, then in that condition it will be a group. It satisfies all fund conditions. It's not just a group, it's also a abelian group or commutative group. Yes, so in general, the set of Zn star, you see this word of star, it means you are excluding non-invertible values, which consist of all integers. I is from 0 till n minus 1, for which GCD of I and n is equivalent to 1, forms a abelian group or commutative group. Yes, it satisfies 5 conditions under the multiplication modulo n. Yes, the identity element in here is 1. This is our 1 ID. Yes, so note that specifically we are more interested to ZP star. What is ZP star? Let's talk about that. P is the prime. What element does it contain in here? ZP star contains anything other than 0 less than p minus 1. Yes, less than or equivalent to p minus 1. It starts from 1, 2, 3 up to p minus 1. Why p minus 1? Because it has to be less than p. And the question is, why am I excluding not excluding any elements? Because you are taking, you want GCD of I and p has to be 1, but p in here is prime. Anything before it, it's going to be relatively prime, so that's why it is all elements from 1, 2, 3 until p minus 1. What elements does this contains? Those elements it contains, yes. And how many elements it contains? It contains p minus elements, yes. ZP star forms a multiplicative group where p is a prime. So now let's talk about a finite group and cardinality. A group G with this operation is a finite if it has finite number of elements. For example, let's say that ZP star. Yes, how many elements does this contain? We just talk about that. This contain all elements less than p minus 1. We are less than or equivalent to p minus 1, and we are excluding 0, so that's why we have actually p minus 1 elements. Yes, this is called cardinality. This is cardinality, number of elements. Or how many elements does ZP contain? ZP contains actually p elements, because why you are including 0 over there? We denote the cardinality or order of the group by denoting this. So if I put absolute value in here, it doesn't mean absolute value, it means cardinality of the group, okay? So the group Zn under the operation addition, what is the cardinality of Zn? We just answered it. Yes, it contains from 0 till n minus 1, so that's why we have n elements. So, and the group of Zn star, what is the cardinality of Zn star? So in here, in order to answer to this question, it is we know that we need all elements such that the GCD of I and n has to be 1. And in order to have this condition, and I teach you that this is Euler's phi function. Yes, this satisfies Euler's phi functions. Phi function. Yes, so we will say that the cardinality of Zn star is equals to phi of n by explaining in chapter 1 homework, the 1.10, I think. Since Zn star is defined as the set of positive integers smaller than n, which are relatively prime to n, that's why it is phi of n. So for example, what is cardinality of Z9 star? This is phi of 9. What is phi of 9? You can evaluate that, or you can calculate it with GCD. How can we calculate it, evaluate that? First of all, we have to rewrite that with 3 to the power of 2. Prime factorization. After you do the prime factorization, it's 3 square minus 3 to the power of 1, which is going to give you 6 elements. Also note that Z9 contains 1, 2, 4, 5, 7, 8. If you calculate it, is 6 elements in there. Also note that this phi function can be written that way, or it can be also written like this. Yes, so if you see that way or that way, it doesn't matter, it is phi function. So you understand that what is cardinality. I hope you saw it previously. Now let's talk about generators. So let's talk about Z11 star. This is a kind of ZP star because 11 is the prime in here. Now what we will do in here is we will take any element from here. I choose A is 3 over here, okay? I choose 3 from here, and I want to see what does 3 generates. What does it mean 3 generates? I'm gonna do A is 3 to the power of 1, which modulo 11, it generates 3. 3 to the power of 2, 3 to the power of 2, it is 9, it generates 9, yes. 3 to the power of 3, it is 27, minus 22, this is going to give you 5, it generates 5. 3 to the power of 4, you can calculate it as 3 to the power of 3 times 3 to the power of 1, which is 5. 3 to the power of 3, we already did it, 5. 5 times 3, it's going to be 15. Subtract 11, this is equals to 4, yes. 3 to the power of 5. What happens with 3 to the power of 5 is, similarly, you can do it as 3 to the power of 4. 3 to the power of 4 is 4 times 3, it's 12, modulo 11, subtract 11, you're gonna get 1. As soon as you got the 1, this is our identity, you will stop it. You will stop it. You know why you will stop it? Because if you proceed with 3 to the power of 6, what happened in here? You're going to have 3 to the power of 5 times 3. 3 to the power of 5 is 3. The 3 to the power of 5 is 1, times 3, it's going to give you 3. Again, you got a 1. You are going back to this number. Yes, so differently saying, let me do differently. After you have 8 to the power of 5, you are going back actually to this number again, and it will rotate. So we have to stop as soon as we got the identity. So what does 3 generate? I'm going to make this kind of notation, just a moment. What does 3 generate? 3 generates over here 3. It generates itself. It generates 3, it generates 9, it generates 5, it generates 4, and it also generates 1. I can write down in order, yes, 1, 3, 4, 5, and 9. And how many elements it generates? 1, 2, 3, 4, 5. This is, I will call it order of the tree. This means how many elements it generates. It generates 5 elements. Why did it generate 5 elements? Because it stops 8 to the power of 5 is equals to 1. Because as soon as it stops, this is going to give you order, okay? This 5 is going to give you order. You don't have to list them. So, and next question is, what if I will do experiment with the order of 2? Yes, I'm going to do the same thing. 2 to the power of 1 is 2, 2 to the power of 2 is 4, 8, and so on. And I see that 2 to the power of 10 gave me 1. Yes, 2 to the power of 10 gave me 1. So I will stop over here. It generates actually 10 elements over here because it stopped the first where it stopped at, it is 10. So thus order of 2 in here is 10. So what happened in here, it generate all element in Z11 star, which is equivalent to the cardinality of Z11 star. What we will call this 2, we will say that 2 is the generator or the primitive element of the group of Z11 star, because this A is equals to 2 is the generate whole group. So we say 2 is the generator because it generates every element inside of the group. If you don't believe me, let's make it the list. Yes, what does 2 generate? Just a moment, let me write down. 2 generates you see, did 2 generates 1? Yes, it did generate 1. Does 2 generates 2? Yes, it generates 2. Yes, did it generate 3? Let's look for the 3. Yes, it did generate 3. 8 to the power 2 to the power of 8, it's going to be 3. So it generates 3. 2, does it generate 4? Yes, it generates 4. And you can look, it generates all elements over here. So it generates whole Z11 star. Yes, so that's why we say that 2 is the generator. So as soon as this satisfies order of the 2 is equals to cardinality of the Z11 star, we will say that this is the generator. Let me go to the definition right now. Definition is order of an element So order of the A of an element A of a group G is the smallest positive integer k such that they satisfy this condition. As soon as you reach 1, you're going to have the order of that one. For example, we just get 3 to the power of 5 is equivalent to 1 modulo 11. Yes. Also, 3 to the power of 10 is also congruent to 1 modulo 11. Also, 3 to the power of 20 is also 1 modulo 11. So, if this is the condition, which one is order of the 3? Order of the 3 in here is 5 because it is smallest positive integer k. Yes, so you are getting the smallest positive integer k. So you don't look to the rest of them. Yes, similarly with any element. And what is cyclic group? Cyclic group, it is a group G which contains an element alpha with maximum order. So what does this mean? That the order of the alpha has to be equivalent to the cardinality of the group. Is said to be cyclic. So if the group contains the generator, then we say that group is cyclic. The elements with maximum order are called primitive elements, yes, or generators. That's what I was talking about. So from previous example, we see that order of the 2 is 10. Yes, so 10 is equivalent to the cardinality of the group. So 2 is the generator of the Z11 star. So we say that Z11 star is the cyclic group because it has generator. Yes, Z11 star is a cyclic group and A is equivalent to 2 is primitive element of the 11 star. If you see this chart, it will give you the idea. For example, if I is equals to 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 modulo 11 is 5. So you see that what does 2 generate? 2 generate all elements over there. Now let's talk about the Morse theorem in cyclic groups. Yes, so note that cyclic group are basis of discrete logarithm cryptosystem. So for every prime p, zp star with under the multiplication is a billion finite cyclic group. Now you know what does it mean, a billion? A billion, it means commutative. Finite, it means that it has finite elements over here, not just a group, it is also a cyclic group. What does it mean, cyclic group? It means that it has a generator and it also satisfies those conditions which we talk about at the groups. Yes, satisfies. Then this is very important, the theorem saying that the zp star is the abelian cyclic finite cyclic group. So it satisfies this 4 condition, abelian finite cyclic group, this zp star. So make sure that because of that we can use for example Diffie-Hellman key exchange and other things, theorems. So protocols, I mean. Let's go to the next theorem. Let G be a finite group, and then for every A inside of the group, it holds that 2 to the power of order of the group or cardinality of group is always equivalent to the identity. And order of the element A must divide the cardinality of the group. Maybe it's not really understandable right now, but if I will do example, it should make more sense for you. So now example is, let's say that Z11 star, you remember that this cardinality number of elements in here is 10 over here. What are the possible orders in Z11 star? So what possible order are in here? So we said that in this theorem, possible orders has to divide order of the group. Yes, so differently saying that what divides 10? What divides 10? It divides 1 divides 10. 2 divides 10, 5 divides 10, and 10 divides 10. So possible orders is 1, 2, 5, 10. It's not possible that 3 doesn't divide 10 or 6 doesn't divide 10. They are not the option. None of them can have those kind of orders. Yes. So let's verify what am I talking about. Order of 1 is 1 because 1 to the power of 1 is 1. Order of 2, we just saw it. Yes, order of the 2 gave me, it generate 10 elements. Yes, it gave me 2 to the power of 10 is 1. Order of the 3, we did it. It is 5. And if I continue, order of the 4 is 5, order of the 5 is 5, order of the 10 is 10, and so on. You see that the possible orders can be only 1, 2, 5, and 10 over here. You cannot have 3 or 6 and so on. So what are primitive elements? Which are generators? This is the generator because it generates whole group. Another one is 6, also generator because it generates whole group. 7 is also generator because it generates whole group. 8 is also generated because it generates whole group. So we have 4 primitive groups. Now the question is how many primitive elements we have or generators we have it. Yes. Next theorem says that let G be a finite cyclic group, then it holds that the number of primitive elements of the group is phi of order of the group. So I'm going to explain to you. If group is the prime, then all elements other than 1 are primitive. I'm going to talk about this in a second. So let me give you an example. Yes, for example, Z11 star, you have 10 elements. Yes, 10 elements in Z11 star. How many primitives you had it? If you check it, we found 4 of them. But this is too hard to do that. Yes, but I can easily use the theorem. I'm going to do phi of order of the group. This is phi of order of the group. It's going to be 10. Yes, 10, I'm going to calculate that. 10 is 2 to the power of 2 times 5. And so this is 2 minus 1, 5 minus 1. This is 1, this is 4. 1 times 4 is 4. From previous slide, you saw that you have exactly 4 elements are generators. Yes, so this was pretty understandable. What is data is asking? The second example is saying that let me do this one. If the order of the group is the prime, yes, how many elements are primitive groups? Yes, how many elements do you have which are the generator, primitive elements? So you're going to do phi of order of the group, which is actually equivalent to phi of p. P is prime in here. So this is equals to Pm minus 1. It means that all elements other than 1 are primitive group. That's what the theorem number 2 says. Yes, this one. Okay, now next example is you did it in you will do it in your homework, that how many elements are primitive groups. Yes, so I want to find how many elements do you have order of 10. We did it. Phi of 10 we did. Phi of 10, it gave you phi of 2 times 5, which gave you the 2 minus 1, 5 minus 1, which is equivalent to 4. Yes. Now, how many elements with order of 10 we did it? Let's do with order 5. You can do quickly. Phi of 5, it's going to be 5 minus 1, which is equals to 4. You have exactly 4 elements with the order of let me do the color, the order of 5. Yes, the order of the 5, you have 1, 2, 3, 4 of them. Now you can do similarly. We are done with 5. Yes, let's go to the 2 right now. How many elements we have with the 2 order of 2? So you have phi of 2, which is 2 minus 1, which is equals to 1. You have exactly one element with order 2. Now, how many elements with order 1? Order 1 is only one element, always, all the time, which is actually the element 1 is 1 to the power of 1 will give you 1. So only one of them. So if you calculate that, 1 plus 1 is 2, 2 plus 4 is 6, 6 plus 4 is 10, exactly 10 elements. And I did one of your homework problem right now. You will work with 53, I just work with 11. And I want to stop over here before I will continue for the next class. Okay.